Thank you, Dave. Morning, all. The title is sort of a bit ambitious, I think. I'd like to actually narrow it a bit and focus mostly on windows and glazing, but you will see there are implications as far as net zero energy houses are concerned. If we consider the typical net zero energy house, if you like, it will have basically two main strategies. First of all, you want to generate energy on site somehow to account for the energy that you will be using. And you want to minimize the amount of energy that you are actually consuming by various means. So just looking at this house here, which is in Cannon Beach, not too far away, you can see it has photovoltaic panels all over the roof to generate electricity. It has this collector here, the solar collector here, to generate heat for both space heating and water heating. And it has lots and lots of windows facing the south, I assume, for daylighting and, again, for heating by direct gain, by passive heating by direct gain. So the typical house, the strategy that we see usually in these houses is we try to harvest energy as much as possible from the environment, and we try to minimize our own energy consumption for whatever reason. Now, there are two elements there, and I'd like to focus just very briefly on both of them. One of them is solar energy, and what you see here is a device for collecting about 1 kilowatt peak of electricity. When I say 1 kilowatt peak, that would be the amount of power generated by this array of panels when it's exposed to 1,000 watts per square meter of sunlight incident at normal incidence to the array. So that is actually pretty much the optimum condition you're likely to encounter anywhere. And in reality, most of the time, the panel generates a lot less. So the panel provides electricity. It has an area for Sdebokale about between 7 and 8 square meters of panels. It costs 2010 prices about $8,000. Prices are going down. And it has an advanced dual axis tracking system. So that generates electricity. The trouble is you need two of those to power one of these little things. That's a portable little electric heater, which you may have seen, or some of you may have in your apartments. And that's because, as we all know, the photovoltaic panels still have a very low conversion efficiency. So that just puts things in perspective. So if you plaster your whole roof full of photovoltaic panels and you've got enough power to generate to run a couple of these maybe, that's assuming you're operating your little heater in the middle of summer at noon. Because if you're in winter at night, it's not going to work. Now, there is another device for collecting about 1 kilowatt peak of solar energy. That's just your standard normal window. It provides heat and light, not electricity, but the equivalent amount of energy is, again, about 1 kilowatt per square meter. This window is about 1.2 square meters in area. It costs only about $500 or $700 as opposed to about $8,000. It does not require a feed-in tariff. Israel has a feed-in tariff to promote photovoltaic installations in residential buildings. So this doesn't require a feed-in tariff. And like I said, it's an area of about 1.2 square meters. The typical window has fixed orientation, no tracking, no nothing. But if it's facing the sun, it will give you about 1 kilowatts worth of energy at the maximum exposure. This is where I branch off to my second introduction. So that was part one of the introduction. Part two is a story that I tell sometimes. It's something that happened to me in reality. I went to a doctor to get my eyes checked, just a standard annual checkup before coming to the States. And this is a very small, pretty shabby sort of waiting room. And there's a receptionist there. And you can see the window in the background. And it's got these Venetian blinds, and they're all rolled down. So I had this interest. I pretty much knew the answers in advance, but I sort of asked the receptionist there, you've got the blinds rolled down. Why are the blinds rolled down? And she said, she didn't understand the question. She said, why should I roll them up? I've got an electric light. So her logic was completely reversed. Instead of having the lights turned on when there wasn't enough light outside, the standard operating procedure was, okay, we come to the office in the morning, we turn on the lights. So I then asked her, do you ever open the window? And then she looked at me and said, why should I open the window? We've got air conditioning. So at that point I asked her, do you actually need the window? She thought about it for a minute and said, no, can do without it. So to summarize, windows are assumed to be part of any normal building. We mostly don't use them properly. And the receptionist here is not actually that stupid, because this window, that's the building on the outside, it's an office building in Beersheba, faces the northwest. This was the afternoon. The sun would have been streaming in. It would have been practically impossible to do any work at the computer display. She would have been very uncomfortable because of the sunlight. It was a warm summer day. And it actually made sense for the blinds to be rolled down. The problem is that once you roll them down, most people never roll them back up again. So she's not that stupid. Now, historically, architects, engineers, whatever, actually gone to quite a lot of trouble to construct windows. And this is a photograph of part of a Byzantine church in Ovdat, not far from where I live, in the desert. And constructing a window is actually quite a lot of effort in terms of building, because you need an arch to support a masonry arch to support the opening. And it's actually much more difficult to construct a window than it is to construct the equivalent area of wall. In modern building, by the way, it's also more expensive. So constructing a window, putting a window in a house is actually more expensive than just a blank bit of wall. But windows provide light. They allow ventilation. They allow us a view outdoors. They may provide winter heating. And generally, we design our buildings so walls are insulated, as airtight as possible. We want to eliminate, if possible, transfer or minimize the transfer of heat either inside or outside through the opaque part of the building envelope. And we use windows to modulate the transfer of light, energy, and so on as the operable part of the envelope. So what is the problem then? The problem is that in sunny climates, and I'll define what I mean in a minute, exposure to direct sunlight may result in visual discomfort due to glare and thermal discomfort because of high radiant temperatures near the window. So you're sitting next to the window, you're not only experiencing the air temperature around you, but also the radiant heat which you're absorbing through sunlight coming into the window and hitting you. So that can result in uncomfortable thermal conditions as well. By the way, there's also damage to furnishings because of UV radiation, which is generally not filtered by normal glass. You can get glass with coatings which filter that out, but most windows, standard windows, don't have it. And large windows also provide, although they provide welcome heating in winter, they also result in unwanted heat gains in summer. So look around you. Most of your big office buildings, even here in Portland, have what is known as solar control glazing, in other words, tinted or mirror glass or whatever, including this building. Now, to define what I refer to as a highly luminous climate or lots of sunlight or whatever, this is a graph that was drawn as part of a project I was involved in several years ago, which I'll be describing in a minute. But it shows you the difference in illumination, that's visible light, measured in Tel Aviv, Porto in Portugal, and Berlin. I'll show you Portland in a minute. So you can see here that Tel Aviv, the global illumination, that's that red line there, and the orange here is the diffuse light, is way more than either Berlin or Porto. That's the Porto global, and that's the Berlin global here in green. The diffuse parts of the light are pretty much similar in all three locations. So the big difference is that because you have a lot of more direct sunlight in Tel Aviv, that means you have changing conditions. So in the morning, your eastern wall gets the direct sunlight, the west and south obviously don't. Then as the sun moves through its normal daily path through the sky, different sides of the building will get exposed to direct sunlight, which means the levels of illumination you're getting are going to vary tremendously, as opposed to the situation we have diffuse sunlight, where it's non-directional, all elevations will receive pretty much the same amount of light throughout the day. It will vary a little bit because diffuse sunlight does. It's not constant. You have more of it during the middle of the day, less, of course, early in the morning, late in the afternoon. But as you can see here, the variations in direct sunlight are much greater in the global, which is mostly direct in the case of Tel Aviv, are much greater than the diffuse. It also means that glare is much more a problem. Now, if you're wondering where Portland would be on this graph, well, that's Tel Aviv and that's Portland. So the purple line here is the global illumination for Portland. This is the global illumination for Tel Aviv. So Portland has surely earned its reputation as a cloudy, overcast city. Just to look at the mean illuminance in Tel Aviv would be about 82,000 lux, and for Portland it would be about 19,000. So even on a nice, bright, summer, sunny day here in Portland, you're still getting less most of the time than we're getting in Tel Aviv on average day. Tel Aviv has about 10 to 15% less sunlight than Sde-Boker, where I live. So where I live, they don't have these detailed illuminance measurements for the whole year, but it's even brighter than Tel Aviv is. So that's the problem. Now, what are the solutions? The solutions traditionally, okay, we've got fixed external shading. This is a pretty bombastic sort of example of immense shading device for Windows. It's in Tel Aviv University, by the way. Much simpler, much cheaper alternative, which is found in Windows in Israel almost everywhere. So simple Venetian blinds externally that you can open them, just open the slats. You've got operable internal shading, which is what most of us use I suppose, in America. I hardly ever see external shading in buildings in America. A lot of curtains, Venetian blinds, and so on the inside. So these are roller shades on the inside in an office building in Germany. Lots and lots of reflective glass. It used to be all the fashion 20, 30 years ago. Today, people are moving more to the tinted glass. All sorts of colors, which are selected primarily based on what the architects like. And you have all sorts of modern, newfangled ideas, which involve switchable glazing, for example, which allows you to change the light transmission qualities of the glazing in response to either the temperature of the glass, the amount of light coming through it, and external electrical controllers. You can play around with it. What all these solutions have in common, though, is one problem. They either block or filter sunlight, or they let it through. And they don't provide a dynamic response to requirements for light and heat that change according to different schedules. Supporting you wanted light but not heat, or heat but you had too much light, you wanted to restrict that. These solutions take heat and light and they do it, whatever they do to it, either filter it or block part of it, they block both parts of the spectrum to the same extent. So what we're looking for is a means of separating these two components of sunlight apart, the infrared part and the visible part of the spectrum, and controlling them separately. So just to define the objectives here, we want, for passive heating in winter, we want the heating component without glare, without the high radiant temperature or the damage to interior furnishings, and we want the reduction of unwanted solar gains in summer. At the same time, not blocking the view out entirely, we want to allow view outdoors, and we want to provide some daylighting. Because otherwise, we might as well be in the position of that receptionist with the Venetian blinds rolled down and essentially no window. We haven't dealt with ventilation, acoustic control. We want it to be affordable and so on. So the problem is actually pretty complicated. So I'll go briefly through two research projects. The first was one that was funded by the European Union. We started it in 1999. It went through 2.5 years, and we looked at a concept that we'd already developed at Seminar earlier, got funding for the EU, went into partnership with a bunch of researchers from 5 other universities in Europe, and did all sorts of things. And we ended up with this glazing system, which I'll describe. The principal operation is as follows. In the winter mode, you have your standard window. So that will be the clear glazing on the outside. And then on the inside, you put in another plate, another pane of tinted glass, and you can adjust or select a tint according to daylighting requirements. The important point is that it's ventilated. So it's not your standard double glaze system, but there's a gap here which allows air to flow freely between the tinted pane and the clear pane. So the clear pane is your normal airtight, weathertight seal, so rain doesn't come in, whatever. And the tinted sheet is your solar control element. And what it does is it absorbs sunlight that goes through the clear glass on the outside. As a result, it cuts down the amount of visible light that comes into the room, but this energy is absorbed in the glass becomes warmer, and it gives off more heat by long-wave radiation and by convection to the air, both on the inside here and also through the air channel here, which is why we want it to be ventilated instead of airtight. And the trick there is therefore to change sunlight from the short-wave part to the long-wave part. That's the heat that we want. In summer, the whole thing is rotated, flipped, so the tinted sheet is on the outside, and now we have the same daylight control, but the energy is now on the outside, as opposed to the winter situation where the energy is on the inside. Having gone through the clear glass, the energy is now inside the building, and in summer it's outside, and it's much easier to remove to the environment when you have an excess of it. Looking at the aerodynamics of it, we want air to flow between the tinted sheet and the clear sheet. How wide should that gap be? 1 centimeter, 2 centimeters, 4, 5, 10, whatever. From a practical point of view, we want it to be as narrow as possible, so the whole thing shifts in some sort of a glazing assembly. We looked at widths varying from 2 centimeters up to about 5 centimeters. The optimum turned out to be about between 3 and 4, depending a little bit on window proportions, but that was enough to have two distinct boundary layers for both the clear glass and the tinted glass to allow air to flow in between. And to smooth the flow, we also added this little round peg here at the bottom. So what you see here in section is that's the pane of glass here, which is the tinted glass, which is being heated. In this case, it's an artificial heat source. In reality, it would be sunlight. That there would be the clear glass. This would be the frame of the window. And air is flowing from the bottom, going up. In this case, you've got smoke here. So you can see here you've got flow detaching at the sharp corner here at the bottom of the glass pane. And adding the round peg here allows air to flow smoothly, and you have a much better transfer of heat from the glass, at the bottom part at least, to the air flowing in the channel between the two panes of glass. So this was a very simple little addition which we made to the prototype, and which later got added to the final production window. This is what the test room, or part of the test room, looks like at Seminar. This is the inside looking out, and that is from the outside looking in. This is still not the full rotatable prototype. This is what we tested, though. So you can see the panes of glass on the outside, they look almost black. In fact, they have a visible transmittance of about 11%. So they're blocking out 90% of the light. They look, just looking at it, they look black. But because it's so bright outside, when you look from the inside out, that's that window there, it looks like it's unobstructed. I definitely would not recommend glass that dark here for Portland, but that's what we use for experiment. And we fit it in with thermocouples to measure glass temperature. We've got a black globe here. This is the backside of a pyranometer to measure the amount of sunlight coming through the system, and so on. Just looking at the results. Glass temperature. This dark tinted glass, which looks almost black, heats up on, this is an autumn day, September, to about 55 degrees centigrade. So you touch it, it's uncomfortably warm to the touch. I mean, it's not like you get a burn, but it's uncomfortably warm. Between 60 and 70 is probably what your radiator, if you've got a water heating system in your house, that's about the range of temperatures that your radiator will be heated to. So it's quite warm. And then this is the inside surface of the clear glass on the inside. So it's a double glazed pane of glass. This is the inside of the inner pane, which is about 35, when that's about 55. In winter, now we've switched the thing around so the tinted glass face is the inside, and this is the room air here. Which as you can see, the room was not heated. It's goes down to about 0 at night, so the room was fairly chilly. So room temperature went up to about 17 or maybe almost 18 here. But you can see that near the window itself, the air temperature was actually lower because it was exposed to the cold outside air. Sun goes up around about here, and then the window starts heating up. And you can see here, this is the bottom. Here, that's the air coming into the window, and that's the top. So these are going up the window. And you can see air coming out at about 30, 37, 38 degrees. So we can heat the air by about 20 degrees as it goes next to that window. And you've got your little completely passive ventilating machine, a convector if you like, giving you air flowing into the room that's heated to about 35 degrees plus. And the rate of the air velocity is between about 0.3 and 0.5 meters per second. So you can calculate the volume of air flowing through that gap there that's about 3 centimeters wide and so on. In terms of thermal comfort, this is the winter mode here. This is the test room, and that's a reference room, a second room, which was identical in every respect except for the glazing system itself. So this is essentially what a person sitting next to the window would be feeling, because they'd be feeling the combined effect of air temperature as well as the radiant gain. So 25 degrees here in the test room, over 40 degrees centigrade. The equivalent, that's not air temperature, that's the combined effect of air temperature and radiation if you're sitting next to that window with standard clear glazing. So you can imagine what it's like sitting at your house, in my home, to have lunch. It's a passively designed house according to all the books and guidelines and so on. So it's got a big south-facing window, direct gain, and I come home to lunch, and the first thing I do is I roll down the blinds because you cannot sit next to the window. It is that hot. In terms of how much light actually goes through the system, so that's the tinted glass. Like I said, it cuts off just about all of it. That's the clear glass, and that's outside, and this is the summer mode. So this is an extreme case, if you like, a very dark glass. The two test rooms, the one with the R system, the one with the standard clear glass. This is the clear double glazed window. That's the window there. The room is about 3 meters by 4 meters, a bit less than 3 meters by 4 meters, triangle. It's a fairly small room. And you can see here this bright spot next to the window, which has an illuminance of over 50,000 lux. To give you an indication of the orders of magnitude, the recommended level of illumination in various standards for illumination of workplaces. So if you take the International Standards Institute standard 8995, for normal work is about 300 lux. Standard office work, between 300 and 500 lux. 1,000 lux is for something that requires really delicate, sort of fine resolution work. And we're getting here 50,000. I would estimate that the room here at the moment has got probably about between 100, 150, maybe 200 lux. So we're getting 50,000 lux there, which is way, way too much. And you obviously not only do not need it, but that's so much you cannot tolerate it. So you typically have this bright spot next to the window, and in the background, in the deeper reaches of the room, the values go down. And what the tinted glass does, it doesn't change the distribution, it just cuts everything down by a factor of whatever, in our case about 80 or 90%. So you still have a bright spot near the window. It's not as bright, it's about 3,000 lux, which is still too much, and about 200 in the side bits of the room. What does it work like in terms of energy? The heat transfer, or the resistance to heat transfer, if you like, of the window, is determined by the clear pane. And the clear pane can be a single glass, can be double glazing, it can be double glazing with low E, it can be any newfangled glazing component you like. And in this case, the test cell that was tested by our German partners, they put in a high-performance clear glazing, a double clear glazed system with very high-quality UV, low E coating. So they had a metric U value of 1.1, which is very good even by today's standards. A standard low E clear glazed element today on the market would have a metric U value probably about 1.8 or 1.7. So this is, even then, was very high performance. But the important thing to note is that the U value for both summer and winter is the same, because it is determined primarily by the clear glazed element. The solar heat gain coefficient, on the other hand, depends on where the tinted glass is. The tinted glass is on the inside, it's in solar gain mode. When the tinted glass is on the outside, it's in the heat removal mode. So therefore, what the Europeans call the G value and what is called here the solar heat gain coefficient changes. So in summer, you have a very low heat gain coefficient, and in winter, you have one that's twice as high, which is the whole point of the exercise. Our partners in Spain drew up this energy simulation software to actually figure out what this window would do when it's installed in a building for a given climate. So you put in a whole year's worth of climate data, and you can actually simulate it. And what you see here is that winter energy performance is essentially similar to a window with the equivalent clear glass element. And the savings are realized in summer by means of shading. So you can see here total gains, total losses. You indicate which are your summer months and which are your winter months and so on. And this is the way I've been showing this slide for the last 7 or 8 years, I guess. And when I was preparing this talk, it occurred to me that this is only half the picture. Because our assumption was that the reference would be a clear pane. Whereas in reality, most office buildings, even here in Portland, have a tinted glass finish. Don't ask me why, but they have a tinted glass pane. So our reference should be tinted glass. And if our reference is tinted glass, then the summer energy performance will be the same, but the savings will be realized in winter. Because that's where, instead of blocking out that heat that you want, you'll actually be enjoying it. Because it's now inside the building, inside the clear pane. It's absorbed inside your weather seal. So the energy gains will be in winter as opposed to summer. How do you actually get a window frame to do this whole rotation thing and still be watertight, airtight, and so on? That was a bit of a problem. And we came up with 2 solutions. One was devised by a Swedish partner who was an owner of a window manufacturing company. And one came to me one sleepless night at about 2 a.m. in the morning. So this is the one I came up. The Swedish one is much more elegant. This one involves a vertical rotator. This is it's quite a complex sort of thing, actually, because it flips out like an awning and then does a whole rotation thing and then locks back into place. So it's quite complex. But we ended up in Israel at least, manufacturing our prototype, which has the advantage of being much simpler in terms of the mechanism. So this is what it looks like in a workshop at the company that manufactures it. And what you see here is this frame here, which is essentially just a gasket. It's a metal frame which holds a pressure gasket in place, no glass there. This is the vertical rotating pane, and this would be the pane with the tinted glass, and you can see here the curved surface top and bottom. And I'll just show you the animation to see how it actually rotates. So what you see here is the summer mode with the tinted glass on the outside, flipping to the winter mode. You rotate the pane, and then the gasket goes back into place to provide the seal. And if you actually needed to clean the gap between the tinted glass and the clear glass, then you could do that as well. So this is how the system works. Part 2. That's a bit extreme. I think most of you don't actually have your desk sitting right in front of the window. And even if you do, most likely you have Venetian blinds or a curtain or something. You're not subjected to that sort of working environment. At least I hope you're not. But I have seen some offices that look almost that bad. And in fact, they're so bad that employees ended up pasting old newspapers on the windows or stuff like that. Go to extreme solutions. So some of you may have actually seen some of those. This is the north facade of an office building in the northern suburb of Tel Aviv. And you can see it's glazed from top to bottom, like most office buildings just about anywhere. And if you look closely, you can see that this floor here and this floor here and this floor here are almost entirely shaded on the inside by what appear to be rollers. And I'll just highlight this in orange. That's the part of the facade that is shaded from the inside. This is the north side of the building, not the west side, not the east side. This is the north side. It supposedly never gets direct sunlight. It's just diffused. It's what the daylighting experts say you should do. And everyone has got their shading devices rolled down because you can't sit and work there. Now, this is a recurring theme. When I went to this office district, I looked at a whole lot of buildings. Almost all of them were suffering from the same problem. Extensive glazing, and people were sitting in their offices and had the blinds rolled down. Now, if you think that's a problem only for Israel, I suggest you have a look around at your own office here in Portland. And I would guess that lots and lots of you have got the Venetian blinds rolled down, and you come into work in the morning, you turn on the electric light. And that means you're not getting the benefits of daylight, or not at least to the extent that you should be. And if on occasion, when I sit in the small seminar room at the end of the department there, if you sit on the side facing the window, not with your back to the window, some days you're lucky enough to get a view of Mount Hood. Most of the time, the fabric roll-down curtain is rolled down, and even then, except on really, really dark days, you tend to see the person sitting in front of you in silhouette, and it's uncomfortable. And that is tinted glass. The bottom part has got sort of a printed sort of pattern on it. But that's tinted glass, and that's Portland. So I would suggest that even here in Portland, an extensive glazed window is a problem for most of you. 4 years ago, we proposed to the Ministry of Energy in Israel a survey and a study to see what could be done about this. And it comprised a survey of real offices, which I will not be showing you, and a controlled experiment, parts of which I'll be showing you. And in both cases, we had a measured record of the visual environment, which is quote-unquote objective, and a subjective evaluation by the occupants. The controlled experiment looked at the effects of tinted glass, the effects of shading and light distribution elements, which I'll refer to in a minute. And it also looked at the location and orientation of the work area with respect to the window. I won't be describing that because that's a whole different topic. So we had two identical rooms. In fact, they're the same rooms we used for the experiment for the glazing system. That's what it looks like from the inside. We put in a sort of simulated, pretty shabby sort of office, but there's a workstation there and a computer and so on. And in one room, we had the subjects sitting at the computer doing various typing, reading exercises, and we were trying to rank performance as well, the typing speed, reading comprehension, stuff like that. And the other room was equipped in an identical manner, except instead of a subject, we had a camera. And we took a series of photographs of what the occupants, the subjects, were actually seeing while doing their exercises. The two rooms had the same daylight environment. And we measured environmental conditions, the illuminance, which is the amount of light coming onto a surface, the luminance, which is what is being reflected or given off from the surfaces. And we took photographs to generate composite HDR images. High dynamic range images are now produced by that. But when we did the experiment, you actually need to get a camera that costs $8,000 or generate them from individual images, which were then put together, assembled together by means of software, which is what we did. That goes to show the rate of advance of technology. So let's look at the effect of tinted glass. The mosaic plot here is actually the entire field of the responses of all the subjects. And what you see here are the proportion of the subjects who gave a certain response here. So if they were very uncomfortable, which is that proportion, as opposed to, say, that's very comfortable. So a small proportion of the subjects said they were very comfortable, and a much larger proportion here said they were very uncomfortable. So the width of the bar is an indication of how many people gave that particular response. The height here is the proportion of the subjects who were exposed to a window with tinted glass as opposed to a window with clear glass. So we could change the glazing. We shifted between subjects and within different series of tests that the same subjects conducted. So we had a fairly large sample. And what you can see here is that putting tinted glass in does not seem to solve the problem. And this is a glass with 50% light transmission, so it's blocking off half the light that would be received normally. So it's not as dark as it did in the previous experiment, but it's still fairly dark. It's what most offices are actually come with today. In fact, if you look at it, there's that whole yellow part there where people are saying essentially we're either somewhat uncomfortable or very uncomfortable, whatever. That's a fairly large proportion. And you can see that the difference between tinted and untinted and clear is not that dramatic. So very uncomfortable, yeah, there's a difference here. There were fewer people who said they were very uncomfortable with the tinted as compared to the clear. But all the other categories, there doesn't seem to be that much of a difference, which means that either 50% light transmission is still too much for Israel, but if you cut it down to a lower level, that means you're employing less daylighting. Or simply lowering the overall illumination level until it's very, very low is not solving the problem. So our original tilted rotating window is only solving part of the problem. It's not really good enough yet. Venetian blinds. As soon as you put in Venetian blinds and the subjects were allowed to play around with the angle of the slats to open, to close, and do whatever they wanted with them, not surprisingly, most of the subjects said they're either very comfortable or comfortable. But once you had Venetian blinds, it didn't really matter if the window was tinted or not, because the Venetian blinds did the work. We already know that the tinting itself does not in itself provide the solution. So, in fact, most of the people were comfortable as soon as they had Venetian blinds. Only a very small proportion were still uncomfortable. Now, can we get both daylighting and shading and so on? Well, here you need to get into this whole realm of light redirecting devices. And the most common and simplest one is, in fact, what is known as a light shelf. And a light shelf can be installed either on the inside or on the outside of the window, and, in fact, both inside or outside, if you like. So all we have here is a light shelf. That's outside, and that's inside. And this is, in winter, we have a low sun angle, and a lot of the light is reflected onto the ceiling of the office space. In this case, the Venetian blinds are deployed, so the person sitting next to the window is actually not exposed to direct sunlight. In summer, you have less light being reflected to the ceiling because the sun is at a much higher angle, but then you can roll up, if you like, the blinds, if you like, because the internal part of the light shelf is actually blocking much of the sunlight. The light shelf we tested had a slightly curved section, both inside and out, to maximize the amount of light. We tested several configurations by computer simulation and came up with something like that. This is a very simple sort of crude device, but you can find them in all sorts of high-tech variants. And the effect of the light shelf on the horizontal illumination of a desk is as follows. If you have no Venetian blinds, just the clear glass, that's no light shelf, and that's with a light shelf. And the difference is statistically significant, and you can see that the median illumination level with no light shelf is about 13,000 lux, and with the light shelf is 3,500 lux. So just putting in a light shelf is actually creating a very dramatic difference here, and it lowers the illumination near the window. If you have a light shelf with Venetian blinds, but the Venetian blinds are only deployed below the light shelf, then you have the reverse effect. Light shelf increases the illumination near the window, which is what you want. You want, when the blinds are down, you want as much light going up to the ceiling, which is what the light shelf does. So here, the result is statistically significant. The median illuminance is, in this case, 792 lux, which is well within the recommended levels. And in this case, 1,200, which is actually even more than the minimum, which is quite nice, actually. So this is essentially light coming in, being redirected by the light shelf to the ceiling, reflected all over the walls of the room, so you get nice, soft, diffuse light, which is very comfortable to work with. You can then take the results of the measurements that we did, or the photographs we took with the camera. You can generate a false color representation of the luminance distribution that we took using the simple camera images. That's what the false color looks like. And you can see these bright spots here, direct sunlight on your keyboard, on your display, and so on. And this is what the computer program, which is not one that we developed, but one which we had access to and used, it actually predicts where the problem areas are going to be. And you can see that it's actually looking, and it actually identifies these bright spots here quite clearly. So you can either by computers rendering, generate by means of programs such as Radiance, an image of the room and figure out where your problem spots are going to be, and then predict what the likelihood of glare being in the particular environment at a particular time. Or you can go to a real office before it's occupied and say, okay, take a couple of photographs, run this analysis, and say, okay, that's where your problem areas are going to be. So let's see if we can do something to improve it. Now, I would suggest that the optimal office window is actually one that incorporates a light shelf inside and outside with Venetian blinds below, possibly retractable Venetian blinds or something at the top. But the important thing is that when architects, engineers, lighting consultants, so on, are designing windows, they should consider the window should have three sections. There's a vision part, which allows you to see outdoors. There's a daylighting part, which should be the part that's above the light shelf, which directs light to the ceiling. And there's possibly also a ventilation segment, which you should be able to operate independently of everything else to provide you some fresh air if you don't want to just breathe the stuff that's coming through the central ventilation system. I could give another talk on what's coming through that. You don't want to hear that one. Just a few final points before I wrap up. Much of the research on advanced glazing system focuses on specific technical aspects. So look at what the glazing companies are thinking of. They want low U values, and they want high light transmission, which is defined by the K factor. That's what they're looking at, mostly. The problems with daylighting, though, are quite often that you have conflicting demands with respect to energy performance, daylighting, ventilation, and typically the glazing solutions that our engineering solutions are providing us are really not good enough. Whenever you have changes in environmental conditions on a seasonal or even diurnal time scale, it was sunny in the morning, it's become overcast now. Clouds come around. You see that all the time. How many of you bother to change the position of your Venetian blinds? I'm guessing very few. Much easier to flip on the light switch, or it's probably on them from the morning anyway. So you should have some sort of dynamic control elements, and they may be operated automatically if you have an advanced computer control system, or they could be controlled by building occupants, meaning you. Which leads us to a dilemma. In public buildings, generally, it's best to avoid systems that require operation by the occupants because experience shows that the occupants don't operate them. On the other hand, our experience also shows that occupants love to have the ability to control them. So put a dummy switch on your thermostat and people will feel much more comfortable. Studies have shown this over and over again. The thermostat switch does not do anything. It's just having the perception, hey, I can control it. Great. So people want to have this, at least this ability to control, even if they never utilize it. There's a bit of a dilemma there. I will skip this one because we're running out of time. And I just want to finish off with one comment. Is it necessarily the individual house that should be net zero energy or water or whatever? And I start off with a net zero energy house because it's a sort of popular concept and sort of fits in with what Dave was talking about. If you do an analogy with water, and water is something that a lot of people find it easy to get a hold of. I do this simple example for my students back home. Let's look at a typical small apartment building. It's 3 stories, 4 apartments on each level. The typical number of dwellers will be 42. Per capita annual consumption, 60 cubic meters. That's about 160 liters of water per day, per person. So that building, on an annual basis, will consume 2,500 cubic meters of water, give or take a bit. How much water do we get? Let's assume we want just rainfall. Tel Aviv has about 500 millimeters of rain per year. Portland has about 900 and something. Where I live, we have 80. So let's take 500. That's half a meter of water. The roof area, 500 square meters. Each of those apartments is about 100 and a bit square meters, which is typical for Israel. Let's assume that you're actually able to harvest 60% of the rainwater because some of it drizzles a bit, it will evaporate, you won't be able to collect all of it, and so on. So let's assume a utilization factor of 0.6, which is pretty much standard for a flat roof in the literature. So you're going to be able to actually harvest 500 square meters by 0.5, that's the depth, by utilization factor of 0.6, 150 cubic meters. You're using 2,500 and you're harvesting 150. So there's a big mismatch there. If you do the same sums for photovoltaic energy, they look even worse as soon as you get into an apartment building with a sort of density that you get in Israel. So you can reduce consumption, you can recycle gray water, you can recycle sewage if you like on site. I mean, some buildings do that. It's more complicated. It can be done. You can increase the utilization factor a bit, or you can live only where there's lots and lots of rain. But even that's not going to be enough for an apartment building. By analogy, in Portland, probably if you live in a standalone detached house, your roof might just be big enough if you cover the whole of it with photovoltaic panels, you might just be able to generate enough electricity if your house was very carefully designed, if all your appliances were very, very sort of high Energy Star rating and so on, and you were very, very careful with how you actually lived and occupied the house. Portland. If you actually lived in those standalone houses, as most people in Portland do, then you actually have the potential to save energy in house heating, but you're spending it on transport. And if any of you have seen this Kenworthy curve here, this shows the urban density, inhabitants per hectare, and this is the transport-related energy. And no surprise to find all the U.S. cities around here, around the top. I haven't been able to obtain the exact number for Portland, but I know that Portland, in spite of having a very advanced rapid transport system in the city, look at the metropolitan area as a whole, 13% actually commute to work on a regular basis using public transport, which is much less than even San Francisco. New York's got about 40-50%. So I would imagine Portland's somewhere around this part of the graph as well. So if you're thinking, okay, let's all build in our net zero energy house, live in our net zero energy houses on a big plot of land, the energy is going there. I would like to conclude by two short comments. First of all, quoting Le Corbusier. Those of you who are students of architecture, which is none of you, he was a very famous French architect who was one of the leaders of the modern movement for architecture. And he famously said the house is a machine for living in. And all too often you find that when you design a building, you sort of consider the technical aspects. So it's a very efficient machine. But you forget the second part of the sentence. It's a machine for living in. And we need to live in these houses, we need to work in them. And that's where all too often our designs fall down. I mean, look at a lot of buildings with a high LEED rating. You find out, go down 5 years down the road, can actually find out how much energy they consume. All too frequently, they consume a lot more than the simulations show that they should. And that's because the occupants are doing all sorts of things that the planners hadn't considered. So you need to realize that to create net zero energy houses, the architects, the engineers, and so on need to recognize that people, we're part of the problem, but we're also part of the solution. And this is a message to all you guys, you engineering guys. That's true not just for the desert. And when you think about it, most of the time we spend our lives in these artificial enclosures, which are pretty much divorced from the environment around us. We regulate temperature, we regulate air quality, we do all sorts of things, and we live in a completely artificial environment. So we might as well be anywhere. That's a bit of an extreme illustration, but that's sort of pretty much the way we are. Thank you. Okay, yeah. Yeah.
When you were going over the effectiveness of Windows and kind of talked about the one being 1.1 U value metric, was that like a center of glass, or was that like overall encompassing the frame and everything?
In this particular case, this was the complete window. What they do in these test cells that the EU has, they have a small building, if you like, which has two chambers. One of them is controlled for temperature, and they have very accurate means of measuring the heat flux from that chamber to the environment. Some of them have what are called adiabatic shells, so only the element that you're testing is actually has heat flux through it. The rest is controlled by means of heating resistance plates, so there's no temperature flow through them whatever. And this is actually the complete glazing system. So that's a very high performance window.
And then kind of another follow-up. I know you guys are using a metal frame for the apparatus that you have the gasket.
Yeah.
Is there any chance you use like a PVC plastic or like a...
Okay, just to repeat the question regarding the frame of the window, which we have with aluminum. in our prototype. It could definitely be wood, PVC. In principle, it could be anything that is rigid enough that is that you could manufacture at a competitive price. The reason we did it in aluminum was that in Israel, that is the standard material for windows. I know that PVC is much more common here in the States and in Europe as well. Timber is probably the environmentally friendly way to go, but in principle, it could be done in any framing material. Yes?
The conversion of energy from high voltage AC mains to the low voltage DC that's required by all solid-state devices, including LED lighting, is like hideously inexpensive and complex and everything. And as compared to if on a local scale, like within a building or something like that, you have a low voltage DC infrastructure. For example, I bought a LED lamp from IKEA. They say, oh, it's 80% efficient on the LED. The problem is that the nameplate power out divided by power in was less than 30%, which meant that the high voltage AC to low voltage DC current wall wart was consuming more than twice the power that was actually being delivered to the LED. Whereas I have working with a modern regulator chip now that claims from a company I really believe 98.5% efficiency driving LEDs. And so if you look at losses, it's like, okay, 70% losses versus 1.5% loss if you have a local power structure based on typically like minus 48 or 48 volt.
Yeah.
Type infrastructure. Is anybody doing any stuff with that?
Just to repeat the question referred to efficiency. Correct me if I'm wrong, I got you on your point. Efficiency of electricity used by modern light fixtures or lighting elements, LEDs, as compared to older generation LEDs, the transmission losses in going from your standard mains AC to the low voltage required by the lamps and so on. I'm not an expert on electric lighting. What I do know, and I'm following the trends, and as I want to relate it to my talk as well, is that lighting fixtures are getting much more efficient in terms of the amount of light output as compared to the energy input. And you look at the old incandescent lamps, they have, I think, about 8 to 10 or 12 lumens per watt. Then the old fluorescent lamps had about 40. The modern fluorescent lamps go up to about 70 or 80 lumens per watt. And the most efficient LEDs are supposed to be up to about 100 or maybe a bit more. This is getting close to where sunlight is, because natural sunlight is about 140, 130, depending on where the sun is in the sky and so on, lumens per watt. So at one point, hypothetically at least, you're going to get to the point where the artificial light is more energy efficient than sunlight, which means that in a hot climate, it's going to be a trade-off between increasing the heat load that the building air conditioning system is going to have to deal with as compared to the benefits from natural light. Having said that, there's always the generation losses along the way, and do you actually measure the whole system, the whole grid, if you like, losses, or you just measure at the point of use? So it gets into a much more complicated question. It does suggest, though, that we need to be very careful about how we design daylighting, because we're always getting heat along with the light. And that is one of the main loads on the main power loads in modern office buildings. The air conditioning system, even in cool or mild climates, is now one of the major users of electric power. Dave, one more?
So I'll start again.
Okay.
So on your reversible window,
Yeah.
I'm curious about a couple of things in terms of where it is in
Okay. Just repeat the question, where we are with that reversible window in terms of manufacture and so on. Second, the risk there of the window not being deployed properly as in winter, summer, and so on. The window itself is actually been through the engineering stage in an aluminum framing company in Israel. And we have prototypes, one sitting in my office. So essentially, if you wanted to, and you put it in order for more than just one, obviously, but if you had a building with 100 windows, you could get them tomorrow morning or within 2 weeks. They have all the injection molds for the window profiles and so on, so you can actually order it. They have not, to the best of my knowledge, they've had some inquiries, but they haven't actually put any up. We actually finished the engineering process a couple of years ago. They have not been, unfortunately, marketing it very aggressively, and they're sort of waiting for sort of some big project to launch it, I guess, which is a bit disappointing from my point of view. But that's the reality. And I could give a whole talk about why green technologies are not being applied in a whole range of different issues. The risk of it not being deployed properly. It's the same as for Venetian blinds. I mean, it depends on the user. And it could quite easily be deployed incorrectly. It could be installed or operated by your building maintenance team, if you like. So it would be done on a seasonal basis as opposed to a diurnal basis. So you wouldn't be able, as the building occupant, to do it on your own if it were to come with a lock. The reality is that it's very, very easy to do manually. So we don't have time, but I can show you a film of one of our secretaries just flipping it around. It doesn't require any sort of very complex equipment. It's just opening a handle, pushing it around, closing it. It's very simple. So in that respect, it should be easy to use at least. But it does require occupant control. Yeah?
I just have a general question on daylighting. Does it matter what part of the visible spectrum you use to people's perception of whether the light is proper?
Absolutely it does.
I mean, if you use incandescent or fluorescent light, that's a totally different look than light from outside.
Absolutely. The question was regarding the part of the visible spectrum of daylight that we use. So yes, it is very important. You want for color rendition to be as natural as possible. You want to have, ideally, a flat transmission graph. So it's the same at all parts of the solar spectrum. In reality, all tinted glass has a slightly variable transmission curve, so it's not a flat curve that you'd like. Some tints are better than others. So the gray tinted glass typically is not color selective, so you don't have issues with people's skin looking yellowish or greenish or stuff like that. So typically the gray tints are best in terms of color rendering, and that is what ISO standard, again, 8995, would probably recommend. So they have a color rendering index, and that would give you the best results. In terms of the artificial light sources, again, you noted correctly, the incandescent light appears warmer. The fluorescent lights, the old ones, are white and cold. The modern fluorescent lamps, some of them at least, are sort of called warm or sunlight or whatever, that give you a slightly more yellowish or orangey color. And the LEDs are pretty flexible. You can get those at all sorts of different colors. They tend to be white, but you can get them a little bit warmer as well. And ideally, yes, you want something that's as close as possible to the natural spectrum of sunlight to get the right quote-unquote colors. Otherwise, you get a distortion, and